Welcome to our lesson 10.4 on hyperbolas, which are another study of conics like we did in 10.3 and have a really similar definition, just slightly different than that of an ellipse. So an hyperbola is a set of all points in a plane in which the absolute value of the difference, so here you can see right here, the difference is constant. On contrary to that, for the ellipse, it was the sum of those distances is constant. For a hyperbola, we're looking at the difference of those distances. And for the structure we end up getting created, looks roughly like two parabolas that are kind of backed against one another. So each of these separate parabolas, they're called branches. But a lot of the same parts we had with an ellipse and kind of with parabolas follow here as well. So if we kind of look down real fast, looking at an example of the hyperbola, which is a combination of both these branches together, it still has a center, just like an ellipse does. It still has a vertex on either side for each kind of pseudo parabola. We have a vertex on either side. We also have a focus on either side. And that focus is where we're doing those distances from. So just like with the ellipse, where we had the center, the vertex, and the foci all in a line, and we either had it horizontal or vertical, we have an extremely similar thing here with hyperbolas. Now, there are a few key differences with the standard form of hyperbolas, where it does look really similar on first glance. We end up having a difference of terms here, right? Because we're looking at the difference of those distances. So where an ellipse was a sum of the terms, for hyperbola, we have the difference of the terms. And where we had these values a and b be from the vertex to the center, and from the center to the edge of that minor axis for an ellipse, for us here with hyperbolas, a is that distance from the center to the vertex, so that's consistent. C is the same as with an ellipse, except for now the focus is kind of on the other side of the vertex. So the distance from the center to the focus is C. And then B for us, we get through a similar, yet just slightly different relationship to what we worked with an ellipse. So when we're working with a hyperbola, we have that C squared is equal to A squared plus B squared. So if I know the distance from the center to the vertex, I can get A, thus A squared. If I know the distance from the center to the focus, either focus, we have C, so that's C squared. And then I can use this equation to kind of fill in the gaps for what I need. If I need to say graph the focus and I have A and B, I can solve for it. If I need to find what that term B is, the right standard form, and I have the vertex and the focus, then I can then solve for that B squared. Now, before we go to the next page, one more difference that we're going to have compared to that of the ellipse is that when we have it horizontal, right, very similar to the ellipse, under the x term we get the a squared, under the y term we get the b squared. For an ellipse, when we change to vertical, we change the placement of a and b. But for hyperbola, when we change from horizontal to vertical, we change the placement of the y and the x terms up top. And if there's a center shift, then that goes along with it. So we'll see a little bit of example of some horizontal, some vertical, and we're going to see that moving on to the next page. So coming on to that next page, we see two different examples. One of the more traditional horizontal hyperbola and its standard form. Again, x term goes first over a squared. And then for the vertical, we have the y squared term going over the a squared. Now, one way to tell, besides just looking at it, is if you know your vertices are going to be in line with one another, or your foci in line with one another from left to right. Well, again, just like with an ellipse, you know that center has to be in the midpoint of those two, and then equally you know it's got to be horizontal. If you know that those values are stacked on top of each other, then you know you can jump to dealing with this transversal being vertical, which is one little typo to fix right here. This should be that the transverse axis is vertical. So let's do an example. Again, a ton like an ellipse. For an ellipse, we needed that A, that B, and that center. No different here. We got a ton we can put down in that standard form. Once we know the center, the A, and the B, then we are good to go to get that standard form. So looking at number one, I'm going to do a little rough sketch just so I get an idea of where these values are placed. So as number one, we have our foci at -6, 0, and +6, 0. So right off the bat, I know two things. One, they're in line from left to right. So our transverse axis, which is connecting the vertices, that is going to be horizontal. So we'll use this for standard form. And I'll just get that standard form down to let us know which one we'll be using. And the other thing we know from graphing our two foci is we know that the midpoint of these two has to be the center. So I also know using this form, my center is going to be at 0, 0. So I know my H and K are both going to be 0. I do need to know A, which we do end up getting right here. We know our vertices are at 4, 0 and -4, 0. So here are my two vertices. So this is kind of the base of those hyperbolas, and they would expand opening left and right in that form. And I know from the center to that is my A value. So for us, we get right here that A is going to be equal to 4. And then I know for my center out to the focus is C. I know that C is going to be now equal to 6. So I got my center, I got my A, I don't quite have B. However, we know from that first page we have a nice little equation to solve for B. We are given the relationship that C squared is equal to A squared plus B squared. So we can then just solve for that B squared. So B squared is going to be equal to our C squared. So for us, that's 6 squared. And that's going to be minus our A squared, which is 4 squared. Well, that just gives us 36 minus 16, which is 20. Now, I know it's habit, right, to jump into solving for B and not just leaving it as B squared, but just like with an ellipse, we actually want what that B squared value is. So we have our B squared, our A squared is going to be a 16, and we have our center. So now we can plug in those values. So x squared minus y squared equals 1. Horizontal transverse axis. So x squared is going to be divided by a squared. So x squared divided by 4 squared is 16. Y squared divided by b squared, which we just solved for, which was that 20. And now we have that standard form. So now we're going to do another example down below in number 2, where we're going to shift that center a little bit, and then we'll kind of flip it and deal with some graphing on the next page. So here for number 2, we already have a ton of information given to us because we already have it graphed out. So we have our two foci at -1, 2, and 5, 2. So that's this point right here and this point right here. Again, if we didn't have it for us already, we could find that midpoint, which would be our center right here. So we already have our center. We already know it's going to be horizontal. So we can already kind of dive into a little bit of filling out this standard form. So I have that horizontal shift of 2, and then vertical shift of 2 for that center. So I'm just going to get that filled out already. And now I need my a squared and b squared to divide by. Well, again, a squared is from the center to the vertex. So I'll just make note that's our a right here in blue. Well, that's just a distance of 2. Again, we could have gotten that from our ordered pairs up here and finding the center through midpoint, or also just graphically. So we see that a is 2. So that means a squared has to be 4. So for this first one, we're divided by a squared, which is 4. And then we have this last little bit to get that b squared. Again, we find ourselves in another position as up top on number 1. We do know A. We know C. We know the distance out to either of our foci is going to be a distance of 3. And then we can solve for B squared similarly as we did up here. So B squared is going to be C squared minus A squared. For us, that's going to be 3 squared minus 2 squared. So 9 minus 4, which gives us 5. So again, you got your center, you got your A, you either are given B, or we can use this relationship to solve for B squared, and we plug in that B squared down below right there. So really not a ton different than what we were doing with the ellipse for getting that standard form. Also, not so much difference as far as the work we have to do for it, except for what we're going to see on the next page, which gives us a little more detail of how we're getting this shape and how it's close to a parabola, but not quite the exact. So coming on to the top of that third page, we have this topic of asymptotes. And as we see here, this little diagram off to the right, we start to see why these look a lot like parabolas, but they're not making that same type of growth as parabolas, right? Parabola always had that constant growth of over 1, up 1, over 2, out 4, 3, 9, had a far sharper curve. And equally, what we haven't talked about so far is what is that B value that we keep finding in an ellipse, right? It was that distance on the minor axis. Now, over here, it has a similar placement on the graph. However, it's what we call the conjugate axis. So that B term that we've been using and finding on the first 2 examples, it's the distance from the center, and if it's a horizontal, transverse axis, which is the horizontal, then if it's going to be horizontal transverse, you get a vertical conjugate axis. And it's just the distance from the center up to this point. This is our B value. And what that B value does, and we also have, right, our A value from the center to the vertex. What these 2 values do, kind of create this little dashed box right here, right? So it's up B, down B, left and right A. We would flip that if it was vertical. And what that box gives us is the ability to have 2 separate asymptotes. One that goes through these 2 corners of the box and go on forever, and then another that goes through these 2 corners of the box and goes on forever. Now you can kind of view it as either 2 asymptotes that cross through those corners, or 4 asymptotes that all spawn from the center and go through their respective corner. Regardless, we can get the equation for these 2 lines that the hyperbola goes out slowly approaching but never quite hitting. So in doing so although it's not the prettiest formulas, we can find those 2 equations. This first we would use if it's going to be a horizontal transverse axis. This second we'd use if it's a vertical transverse axis, which is the difference of that slope we get created. It's either B over A for the horizontal or A over B, and that just comes from that rise over run. And we can be given these formulas of the asymptotes to help us graph. We could have the graph, create these. We know a little more specifics of how that growth is happening on those hyperbolas. And although, again, it's not nice looking, it's just substituting in those known values. So that H comma K, there's our center. So if it's at 0, 0, those just disappear. And then that B over A, we can get straight from that standard form or from any of our known values using that equation that's going to be that C squared equals A squared plus B squared. So let's see an example of this in motion. So here on number 3, we have an equation, not quite a standard form of an equation just yet, of a hyperbola. And right off the bat, just like an ellipse, we know these always need to be equal to 1. So I'm just going to make a quick change on this one before we start dealing with sketching and finding these values. I'm just going to rewrite this into our standard form, where I'm going to divide by 16 everywhere on both sides. So that's now in the standard form we're more used to. And since we're kind of going backwards, we're going to find the vertices, find the foci, graph it out. I'm going to take this from that standard form and change out the denominators just slightly. So instead of 4, I'm going to represent that as 2 squared, so my a squared. And then instead of 16, I represent that as 4 squared, aka 16, which is our b value. So now we can kind of work simultaneously, filling in some values, graphing them simultaneously until we get the entire graph of the hyperbola, and then also all these known values. So for us, we have no shift from the center. So then we know our center is going to be at 0, 0. So there's our center at 0, 0. Our vertices are a away from the center. So a for us is 2. B for us is 4. So 2 to the left and 2 to the right, since this is going to be a horizontal transverse axis. So 1, 2, there's a vertex. 1, 2, there's a vertex. So that's happening at positive 2, 0, negative 2, 0. We then know our foci are happening C distance away. So before we do that, I'm going to use that B value. So again, that B value was that conjugate axis, so the distance from the center up and the center down. So we'll go up 1, 2, 3, 4, make a little point. 1, 2, 3, 4, make a little point. And it's within this box right here that's framed out by the distance A and the distance B that we're going to end up making our asymptotes through, but we'll wait until we get to that at the very end. So we want to do foci next. But to do foci, we need to know that value for C. Now we have A and B, so we can use that formula. C squared equals A squared plus B squared. So for us, that's going to be C squared is 4 plus 16, which tells me that C is going to be equal to the square root of 20. So again, it's not the prettiest number, but that's totally fine. Square root of 20, that's just between 4 and 5. So I'm going to go out. That's 1, 2, 3, 4, almost to 5. So I'll have one focus right there. And then similar on the other side, another focus right there. A reminder for the hyperbola, the vertex is kind of on the inside between the focus and the center. And that's not too bad. We can write down the points for that. It's going to be 0 out, positive root 20, and then 0 back, negative root 20. So we have our 2 ordered pair for our foci. And now we want to get the equations for our asymptotes first. And then I'll kind of verify that's looking right as we graph it. So for our asymptotes, we have our formula from up above. Kind of bring this down. If a transverse axis is horizontal, we get to use this formula. Now, for us, our center is 0, 0. So when I write this formula down, I'm going to have no k. So we're going to have plus and minus b over a. So for us, b is 4, a is 2. So y equals 4 over 2, y equals negative 4 over 2. I'll get both of those separately started. And then h is 0. So we're just multiplying that by x. Now, we would usually simplify this, right? This is going to be y equals 2x. This is going to give me y equals negative 2x. So both of them have a y asymptote of 0. Or sorry, not y asymptote, y intercept of 0. So from 0, 0, if I were to go, say, up 2 over 1, up 2 over 1, we end up hitting that corner, which is exactly what we'd expect from the first asymptote. And then again, starting at 0 with a slope of negative 2 over 1, negative 2 over 1, we end up with that same matching asymptote that, yes, we could have graphed right here just going, of course, it's going to go through that corner. but we just want to be sure we get that formula so we can use that slope-intercept form just to double check we have those right asymptotes. So we'll run through one more time. Found our center after it's in the standard form. Change our denominators to kind of their squared forms, so 2 squared, 4 squared to get our a and b. A, that helps us get the vertices. It's our distance from the center for our vertices. B helps us get this conjugate axis distance we go out. We use this equation here to get our C value, which helps us get our 2 foci. And then lastly, we use the equations up above to get our 2 asymptotes. Now, the last thing to do is start at either of our vertices we have here, and then similar to the shape of that parabola, we just work our way towards the asymptotes up and down, and we do that on both sides. So it seems like kind of a lot of steps, but a ton of it mirrors from that ellipse. So although the next one's going to be a little bit more challenging, I'm going to have you guys give it a pause and give it a shot. And I'm going to make one change to make life just a little bit easier. So going on to that last page for number 4, I'm going to change this 144 right here so it fits a little bit better on this graph. We're going to change this to divided by 16 for us. So again, the x term is first, so it'll be a more horizontal hyperbola. We do have a shift in the center, so keep an eye out on that. But do the best you can to kind of just use those formulas we have, get down those ordered pairs we need, and then we'll come back together and see how you did. So coming back to that last number 4, hopefully you gave it a pause, gave it a shot. So a few things to get down. Again, we made that change of that a squared being 144, which would have made a 12, to 16, which gives us a is 4, and then here we get b is 5. Now from here we also have a shifted center, so it's to the left 3 this time and up 2. So here we get that shifted center. And then because it's x squared first minus y squared, that's horizontal transverse axis, so horizontal hyperbola. So from the center out a, left and right from there give us our vertices. Well, if we go a shift of 4, we end up at -7, 2 to the left and 1, 2 to the right. Now with a and b, we can solve for c. We end up with square root 41 when we do that. Again, square root 41 is not the prettiest, but that's a shift of not quite 7, not quite 6, somewhere in between. So from that center to the right and to the left, square root 41 is about 6 and some change. So we have our 2 foci. And to get that ordered pair, granted, we're not using it too much for that foci. We're just kind of recording it. It's whatever that original x value is, so -3. And then we're either going positive root 41 or negative root 41 from that point. So the ordered pairs of the foci aren't the nicest looking, but definitely can get a decimal if we wanted to for helping graph that. Lastly, we use our 2 formulas from that page before to get our 2 asymptotes. So we end up with 2 plus 5 over 4, so k plus that b over a, so b over a, 5 over 4, times our x minus h, but for us that's x plus 3. So we get the positive version, and we get that negative version. So with that a and b, we kind of get our little asymptote box started. So from that center, you have your 2 asymptotes that run corner to corner and all the way through. And then that last touch is the start at each of those vertices. And similar to the shape, but again, not quite the same as a parabola, work your way out towards that asymptote and along it, and you do that for both of those. So that wraps up as far as we're going to get with dealing with hyperbolas and conics for this year. But one little fun fact, kind of just at the bottom of your page, for any of those who are into astrophysics, is that all of the orbital paths of all of our kind of astral objects, be it planets, suns, the galaxies, asteroids, all of them follow one of our different conic sections. So with the sun as a focus, say for our solar system, there's a vertex point off of it, and things either have an elliptical orbit, a parabolic orbit, right? And that just kind of means it's come in and kind of shot back out into space, kind of not to return, or a hyperbolic orbit. And mathematically, we model that through those different sections. So, fun fact of conics that the next time you end up seeing it, you'll get a little deeper into and hopefully can explore some topics like this.